want to say welcome to this workshop called Machine Learning and Drug Discovery on the context of this beautiful project called First Latin American Congress of Women in Bioinformatics. I guess that the abstract about me is that I'm working to make a scientific who develops software for chemoinformatics and drug discovery. And this includes many things like machine learning, docking, etc. And I really hope that in the next years I could do this uh, this objective: develop software for chemoinformatics. And here are some ways that we can keep in touch. Well, of course, if you want. But right now, I want to ask you a favor. We want to know you. I'm asking you to send on the chat of the Zoom room your name, your city, and your country. This is because right now we are here from different cities around the country and from, around the world. I guess that here are students from Chile, from Estados Unidos incluso, and of course from a lot from Mexico. Uh, you can write also about your education, your motivation to take this course. And if you want, we can keep in touch. You can share your Twitter, your email, or any kind of social media. I'm going to wait a few minutes to see on the chat this information. Well, of course, this is just if you want. I mean, so the outline of this workshop. First, I'm going to make a brief introduction of machine learning, then a quickly Python crash course around like 15 minutes. After this, we are going to take a break to take lunch, and then we are working with regression algorithms. After, we are going to practice some decision trees and random forest models, and finally, we are going to work with a classification algorithm. So, in the concept of the introduction, I guess that it's a good idea to work first about artificial intelligence. This is a concept that is all around, is always present on research and also the industry, because it's an effort to automatize intellectual tasks normally performed by humans. Some common employments of this technology is classify images, and this is why sometimes we can think that Google knows always where we are, but also it's very common use artificial intelligence on speech recognition and translate text. Well, I guess that in this room we have all use Google Translate. So artificial intelligence will be used by humans as a tool to augment their capabilities. I like very much these phrases because sometimes we think that machine learning is going to do our work. In some cases, this is true, but the main objective of artificial intelligence is do the things that we cannot. Artificial intelligence includes also machine learning and deep learning. In the next slides, I'm going to define what machine learning is. So here is a good idea to talk a little bit about Alan Turing and their work computing machinery and intelligence. He defined a concept called the Turing test, when the main idea is that computers could simulate the capabilities of humans. This is a key concept that will can to shape the artificial intelligence. So I guess most of you have some experience writing scripts or writing some programs with a programming languages. What we do when we are working with the programming languages is we write a program to get the answers. And we say, oh, well, it works. But it's not that simple. So how does a machine learning system works? We have our input, our data points, and we train our model to get some results. This is very similar to the past slide. So the magic or the objective about develop a machine learning model is transforms its inputs data into meaningful output. So really the problem here is get meaningful results. No, sometimes we can do this, or we know a very experimented scientific who just see the molecule and say, no, this is not going to be soluble on water. But come on, they have been working by 30 years. And if we know the data, we know data about solubility, we can train a machine learning model who defined who help us to identify if our molecule could be soluble on water or not. So this is why I say that it's not necessary that a machine model is going to say or work for us. It can help us, but definitely it cannot replace. So does someone have any question? I can see the chat right now. Well, continue. So what's learning? I have here some pictures. For example, in this plot we have some sample. We have a scatter plot of some sample data. We have black points at one point, and here is very easy to identify two different types of data. But it's not always is very easy. So most of the machine learning models I know, or that they exist in general, use a coordinate change system to make a better representation of the data. Yes. So I'm going to work a little bit about learning of the next slide, but I want to tell you now that about a brief history of artificial intelligence. First started some probabilistic models like the Bayesian model. Next, at the 80s, for example, they started working with early neural networks. After the mathematicians developed one of my favorites, the kernel methods. Then some common algorithms developed for decision trees, random forests, and the new one who rules a lot, the gradient boosted machines. Then it was identified that it get very popular, the neural networks who correspond to the deep learning models. And the landscape also includes all of them, because it's not necessary to profile the data a lot. But these tools are not new. What is new is the easiest way we can implement in our projects. But why right now in the time it's very easy to implement machine learning models? Mainly by the hardware. Even in a laptop, we can train several models. Also, now we have more data than in any other point of the history. I mean, we can go to Drupal Bank, to Sync, and to many other databases. And this does not exist 20 years ago. Of course, now we have more advanced algorithms, but some other things that have helped a lot with the machine learning democratization are the simplicity, not the simplicity of the algorithms, I mean the simplicity way they can be implemented, because there are many libraries like scikit-learn, that is the one we are going to use all around the practical session.
Sorry, Barbie, and sorry for the interruption. We have two questions in the chat.
Okay.
One from Ale.
Uh-huh.
It's does the transformation of coordinates is always a linear transformation, or could it be a non-linear?
This is the magic of machine learning. Because if it's always a linear problem, we don't need machine learning. I mean, we can do it with a calculator. The machine learning models can identify patterns that are not necessary, obviously. And there are many ways. There are dimensionality reductions. There are circular coordinates. So in a little bit moment, we are going to see that there are different algorithms, and they can be applied to many different types of problems.
The other question is from David, and he asked about data profiling. Sobre qué se entiende por perfilado de datos.
Okay. Well, for example, sometimes sometimes we have data in different scales. For example, we have the log P activity, and it's about in a range of 2 to 3 points, etc. But we also have, for example, the molecular weight, and we are talking about 200 to 500, and this and now with the computer, it's very easy to scalar all the data to be on the same time of data. Well, this is a process that also includes some other things, but this is basically the idea. So, for example, when we are working with categorical variables like I'm agree, I'm not agree, I'm disagree, this could be hard. It could be hard for a model to process text data. But what we can do is to make agree 3 points, not agree 0 points, etc. So this is the process of profiling data. And this also includes that sometimes there are data missing, and we should make an imputation of the data. And also we can, for some models, it's necessary to remove outliers. I mean, outliers are data which very different from the mean of the data set. And this is the mainly idea of data profiling. Is there any other comment?
No, that's it. Thank you.
Okay, it's just I cannot see the chat on my
Don't worry, I'll let you know. I'm looking at it.
Okay, thank you very much, Agustin. So, well, I guess that information with simplicity, it's okay. It's okay. Now I want to talk about another important thing, that is the scalability. I strongly recommend to you that when you are training your models, you can start, for example, with 100 compounds. Of course, your model is not going to have a highly performs, but you can you can manipulate the type of data. You can adapt your code easily. But if you can do it with 100 compounds, you can do it with 1,000. So it's very easy right now to work with very big data sets of compounds. This is what I mean when I speak about scalability. And also, the models the models are very versatile and very reusable. You can, for example, use the same workflow to predict, for example, the activity of compounds to for one target and for any other, but the idea is completely the same. So I want to make emphasis in that we need to know very little about Python programming to do research using machine learning of the learning. Well, in my case, I like very much to code in Python, but also there are very libraries for R, for example, or right now Julia programming language is getting too much attention. So you don't need to be an expert coder to implement this model on your research. So one of the most common ways to classify machine learning models is about the way they learn. So basically, basically there are two mainly groups: supervised learning and unsupervised learning. The supervised this it's almost a stupid thing, but supervised learning is when you know the labels of the targets. So you already has a previous information on this topic. And unsupervised learning is when the model is trained and after is capable to predict their own labels. So basically, labels are not known. So the unsupervised learning also have some subclassifications that, like clustering, which is a method that try to detect some group of familiar visitors. For example, let's suppose that we have a blog and too many people watching around the world, so we want to identify some characteristics of these groups, the range of the rango de edad, for example, if they are women or women, if they are students or they are professionals, etc. A very common tool in drug discovery is the visualization and dimensionality reductions, because these algorithms helps for example, when we have complex data like theory or more descriptors, we can just visualize the chemical space in a dose dimension or 3-dimension plot. So this is very useful. And finally, another one is the association rule learning. This is not very common, but this this refers to some rules of classification. For example, is a student or not? And you are going to profiling and getting clustered your data about some pre-identified rules. Sorry. So now I want to mention some of the most common machine learning supervised algorithms. I'm not going to say a lot of any of these because I prefer to do it on the practical session. But I guess it's important, you know, these algorithms correspond to specifically this kind of type of learning. Some well-known and identified examples are from supervised learning are Canier's neighborhoods, who tries to identify the compounds who are close on the hyperspace. A very well-known and a very useful is linear regression and their homology logistic regression. With linear regression, we can predict a continuous value, I mean 1, 2, 1.1, etc. But with logistic regression, we are going to identify classes. For example, is soluble and not soluble, or it has activity and it has not activity. One of one of my favorite super vector machines, who also helps to identify compounds in different classes. Decision trees and random forests. Decision trees are very helpful to explore the data and identify some particular differences. And finally, neural networks. Of course, we are not going to do neural networks in this workshop because this will be, this take more time. So those are the most common supervised learning algorithms. So let's continue to some example of unsupervised. For common clustering methods for unsupervised are also k-means, hierarchical cluster analysis, and expectation and maximization. All these help to identify some particularly groups around the data. But here remember that we don't know the labels. The labels are identified by the difference of the data. And about visualization and reductionality dimensions, we have the principal component analysis and the distributed stochastic neighbor embedding. Both of them are very common techniques to visualize the chemical space, for example. And we also don't know the labels. So now we have that different machine learning algorithms from different data. And the logical question is, how choose the right model? It depends. So it depends of what? Basically of two things, of what are we looking for? Because sometimes we say, well, I want to do machine learning. Okay, but maybe you can resolve your problem just with a scatter plot. So it's very important before start training models to be sure of what are we looking for. And the next important thing is what information is available to me. Because of course, if we don't know the models, we cannot make supervised algorithms. Uh, Here, I want to use this roadmap. You can find them on the page of Scikit-Learn. I want to use it because honestly, I couldn't have do it better. So let's going to see some examples. I mean, this looks like Jumanji or something. For example, if we have more of 15 samples, it says, well, yes, you can try. If you, for example, do make the question, are we predicting a category? Yes or no? If the answer is yes, do we have the label data? Yes. Well, no, you can use a classification model. And even if we are using classification models, there are many different types of algorithms we can use. We can use supervector classification, supervector regression. Also, we can use another approach called naive Bayes or a kernel approximation. But what happens if we do not have the categories? If we do not have the categories, the logical question is, do you want to predict a quantity? If the answer is yes, we can make a SGD regression or a supervector regression or even a linear regression. But, well, you're not looking for, you don't have label data and you don't want to predict a quantity. What want you do? Maybe we just want to make some dimensionality reductions to find to find information or to find similar components around the space, or we want to classify in different groups or data by making some clusters. So I like very much this image because it can be very helpful to decide which model or which algorithm is the appropriate for our data. So let's remember that some slides ago I said that we need three things to make machine learning: input data, example of expected outputs, and a way to measure how it's going the training. So we also know that different algorithms are useful for different problems. And now I had a new question. Are the evaluation metrics the same for all the algorithms? And the answer is no. In a very simple way, I can tell you that regression and classification has their own metrics. For regression, those are the most commonly, and for classification, those are the most commonly. And this is very important because they are ways to describe the algorithms, but they tell very different information about the model. So I also prefer to discuss this on the practical session. And now I think that we have talked a little bit about machine learning, and so now it's the time to make the switch and think about how can we implement this on chemoinformatics and drug discovery. So in the last years, we have seen the increase of publications and study cases that employ machine learning and recently deep learning to chemical analysis. And I guess this is a way to say that this is a very useful tool. And another thing I want to emphasize is that those are efforts that are made at the industry and also in the academia. We can see some papers of Pfizer, and we can see also so many papers from the academia that use those that merge those tools. So not no, I want to also introduce the concept of chemoinformatics, that it's a discipline that employs equations, model, and computational techniques to apply chemical tools to apply chemical tools and computer tools to solve chemical problems. So it seems that we are on the same things of models, and this tool was also developed at the industry, and the mainly objective it was to storage databases and manipulate chemical structures with computers. So it seems that chemoinformatics and machine learning should be friends. Is there any other question? Agustin?
So far, so good.
Okay. So the process that we should go to work on a chemoinformatic project is the extraction of the data, chemical data, of course, process them by any way or any form we have decided, and finally, the extrapolation of the data to make predictions. So this looks very much like a machine learning process. And the main idea of chemoinformatics is get valuable information from chemical structures. So at this step, it's very important to use machine learning, because if you use machine learning in chemoinformatics and specifically in drug design, we are going to develop best model, and we are going to make better extrapolations. So this is a paper I strongly recommend you to read. It's a review called Machine Learning in Chemoinformatics and Drug Discovery, and here they explain the relationship and the employment of machine learning tools on this science area. And it says that machine learning use recognition algorithms to discern mathematical relationships between empirical observation of small molecules and extrapolate them to predict chemical, biological, and physical properties of novel compounds. This is a very better way to explain the past slide. I hope you will agree with me. No, I'm going to start with some particularly tools that use machine learning on drug design. One, well, I mean, both who are very common are the QSAR and the QSPR. QSAR is a mathematical way to identify quantitative structure activity relationship, and QSPR refers to identify property relationships. So both have been very used in the past years. I mean, like 10 years, and these are very powerful tools on drug discovery to predict biological activity, add descriptors, and recently toxicity descriptors. Recently, the toxicity descriptors, the use of machine learning to predict toxicity has increased very quickly, because it's it's cheaper to develop a model that trained with many animals. And another very important field on this is the interactions. It's the prediction of interactions between drugs. Of course, this is not very easy, and there are not a lot of data on these topics like in biological activities, so it's more hard to perform some these kind of problems. And the necessary tools to implement these models is, of course, advanced chemoinformatic and machine learning techniques that are capable to modeling non-linear data sets. Well, if all of this were, if we have linear data, the life could be more easier, but probably our job wouldn't be necessary either. Um, a concept we should not forget to do machine learning is the big data. That is a way to deal with very big data sets. And well, this is the most common way to implement machine learning in drug design, but it's not the only one. Recently, I was reading that machine learning has also been employed on molecular dynamics. Molecular dynamic simulations are important tools because describe the evolution of a chemical system in the time. But we also know that this technique has several disadvantages because they
Bárbara,
use.
we have a new question.
Okay.
What do you mean with interactions in drug discovery? Do you refer intermolecular interaction, H bonds, VDW, salt bridges? It was asked by Arley.
Uh, can you repeat? I couldn't hear the last part.
What do you mean with interactions in drug discovery? Do you refer intermolecular interactions like H bonds, VDW, salt bridges?
Well, to be honest, this I wasn't here about interactions of each bonds, but I guess that this could be made. To be honest, I was talking about metabolism interactions. For example, when you use a molecule who inhibit a CYP protein, and, and for patients who take two or more drugs, we can uh, we can predict if at the metabolism phase it could be a problem if a person take two or more drugs.
Okay, and David Davila, he is asking, can you mention the computational limitations, please?
The computational, the computational limitations of molecular dynamics.
Yes, I think so.
Okay, the computational limitations are that, well, I need some help. Uh, okay, it's very hard to describe the accurate electronic structures, and also it's very hard to describe the empirical fires fault. Um, this process cannot be done in a simple CPU. We need some graphical process to make this analysis, and machine learning can be used with CPUs. Uh, is it clear?
He didn't answer, but I hope it is.
I hope. Well, if you have any other, well, I'm not an expert in molecular dynamics, but if you want, you can send me another question on the chat or on the email, and we can discuss it about. So all these things, the potential energies and the force field, are very hard to compute for a, and sometimes the potential energies should be computed each time we run a molecular dynamic. What machine learning tries to do is it's by automatically tell you some of or automatically predict some of these values at only a fraction of the original computational cost. This is because maybe we can do a dynamic with a single protein for a single ligand, and the idea is that if we have a similar ligand, but it's not the same, we can predict some of these parameters from a past experiment. So this could be this is a file who is growing very fast, and I guess that in some years it could be very easy to do molecular dynamics research. So we have been studying, and we have been talking a little bit about the process of make a machine learning project, and I include this slide because I guess it's very useful to identify the data representations. I mean, for me, this color I call them aquamarina, but when we use different categories, it has very different ways to represent them. So the same happen when we want to talk this color. Right now it's going to be a molecule, and we have molecular structures descriptors, the formula in 2D dimensions, and for these and these are exactly two different ways to describe the same. Is, for example, this configuration and these hex representations are two different ways to represent a color. Well, we does not work with colors. We work with molecules. So some molecular descriptors that we need to compute to fit our model with input data are constitutional descriptors, electronic, geometrical, solubility, etc. We should also make data preprocessing. This is also the same that the data profiling, and after we can do multivariate analysis or a machine like with very different algorithms and evaluate our model. So I guess that this workflow represents very well the information we have been discussing. So finally, I want to show you some successful case of the machine learning implementation on drug discovery. I guess everybody knows SwissADME, who is a server that predict some molecule that predict very descriptions to describe the ADME process of a molecule. If we insert a molecule here, we get all these results. And guess what? Many of these descriptors are computed using a machine learning model. Specifically, when we see the result of this protein, well, when we see the result of if this molecule is going to inhibit this specific zip? The answer is yes or no. And the way that we get this response is by the use of a super vector machine, which area under curve is of the dot 9. And another important thing about this server is that it's very well documented on the article, on the material suplementario of the article, and you can find all this information. For example, the solubility water was also computed with a linear regression, and the way they used to say that this was the best model was an accuracy value. Here is the reference of the article, if you can read them. And another example.
Sorry, Barbie. There's a question from Cecilia. She asked, in the case of detecting outliers, what could be done?
Generalmente, la mejor manera es quitarlos, to take them away. Of course, we have some rules to detect outliers. For example, the three standardization or things like that. But these cut-off lines should be maintained for all the descriptors. Any other questions, Agustin? So, well, we were talking about another successful case, and the case I'm talking about is on this article, and they work, or the problem the problem that they tried to solve was make a biological activity prediction, and they identify the labeled as with like positive prediction and false positive activity or false activity. So this is important because they represent the molecules with different fingerprints, and they analyze the relevance of the different fingerprint features, and in this way they could identify the molecular regions that are more important for the activity-based classification. So the thing I like about this project is that they develop a model to identify if a molecule is active or not active, and also on the way they identify the most important features that gives the molecule the activity. So those both meaningful information in a single project, and they basically use super vector machines that we previously saw that it's a supervised learning technique. So about the introduction, practically this is everything. We can start with the practical sessions, and remember in this GitHub, I guess, was on the email, but you can see this. You can see here. I'm going to share these slides also to you. And well, if now we are going to start with the practical session. This is going to This is going to take part on Python, and I'm going to use Jupyter notebooks. And if you didn't install the requirements that we send you in on the email, I strongly suggest you do not try to write the code at this time. because maybe some dependencies are not going to be available and you are not going to be able to run all the code. So I guess it's better, a cool idea. I guess it's a better idea just to follow the workflow on my screen. And if you have some problem to replicate on your computer on the next days, you can send me an email and we can make, for example, another Zoom session and help you to install the requirements on your computer. Because sometimes install the requirements, it's a very hard work. Okay. So I'm going to share my screen again. Well, does someone has any questions about the introduction? I also want to apologize for my English. I practice very times the presentation, but I try to do my best, but I am not a native English speaker. And also, I want to say that the reason this workshop is on English is because we have people from Brazil, and we do not speak Portuguese, and I do not speak Portuguese, and this is the main reason this workshop is taking place in my bad English. Your English is... Okay, so I'm going to share my screen again. Here. Okay. The best way to manage environments and install machine learning dependencies on Linux and Python is the use of a library called of a manager packages called Conda. Right now, I have everything installed on my computer, and I'm going to activate my environment using Conda.
Arley has a question. He would like to know if all the requirements for the session are available for Windows, because he tried to install some of them and had problems with sticky learn.
With scikit-learn.
Sticky, sorry.
To be honest, I prefer to use Linux. It's for long more easy to install everything on Linux than in Windows. Oh, well, if you do not feel ready to do that, you can use Colab, for example, and or we can have another meeting, and I can help you to install the requirements. But I strongly suggest you seriously think about change your operating system. I can find the Zoom.
Just a comment. I've tried. I'm using Windows. I had installed Anaconda, and I tried to install all the dependencies and the libraries that you suggested. I think it worked. It worked just fine, but I haven't tried with the workshop instructions. I think the installation works, so maybe it's just a simple thing.
Okay. So, well, this could be an option. If you are sure or the dependencies are installed, you can do it by yourself. But if you don't know if they were working properly, I guess it's better you can follow the instructions on my screen. Also, I tried to use a binder and we could be all in the same page, but I couldn't set up the variables on a binder. I'm sorry. Okay, so as I told you, I previously installed all the requirements on a Conda environment. I'm going to activate, and for example, I'm going to show you some of the libraries installed on my machine. For example, sklearn, and Matplotlib should be also here. Scikit-learn, NumPy, we are going to work with NumPy and Pandas. Basically, those are the most important for our job right now. Okay, so now I'm going to open my Jupyter notebook. These files are all in the GitHub repository. You can download from GitHub, and well, I'm going to work in a very quickly Python crash course. I'm not going to tell you all about Python, but I'm going to tell you the things I'm sure we know to perform the practical sessions. For the first thing I want to discuss is to create or to define variables. The variables are containers to store data values. For example, here I'm defining the variable a by using this symbol. And if I want to visualize this variable, in Jupyter Notebook, there are two ways. I can just write the name of the variable, or I can use the Python command called print to visualize the result. Both are allowed on Jupyter Notebook, but of course it's easier to do the job on this way. So the variable is created. At the moment, we assign a value. Sorry,
Barbie. You're just sharing the Unix screen, but not the Jupyter screen.
Okay, sorry.
We couldn't see that.
Yes. Can you stop sharing my desk?
Yes,
please?
sorry.
And do it again. Okay. Hi, everyone. Okay. So, are you watching the Python, the Jupyter Notebook?
Yes, great.
Yes, perfect. So I was talking about those variables and the way to define that when we use the equal signal and we write a specific value, we create the variable, and there are the two ways that to visualize that I say before. No, another important thing to know is that Python can allow several different data types. For example, in this case, I will define the variable with a string value. But also Python allows to storage numbers. These numbers can be integers, or they can be float numbers, and even we can use complex data, but to be honest, I have never used complex data. And also we can define variables like list, tuples, range, or dict that allow to storage many components at the time. For example, I'm going to define the variable doses, which is equal to 200. To get the data type, I'm going to use the method type. Oh, well, what do you expect we get when we run this cell? An integer, a float, or a string? It's a string because it's a string of characters. And here, of course, it's not a string, it's an integer. And we could do this all the day. But next move to the next thing we need. In Python, there are some operators that allow make some comparisons between different variables or some different mathematical operations. For example, in this case, we are going to print the sum of variable x and j. The result is 15. This is very easy. And this is another important thing, because now in this cell we are asking Python if variable g is equal to variable x. Of course, the result is false. Okay. No. About the Python collections, we are going to define a list, which is a collection of ordered and chunkable data. And an important thing about list is that it allows duplicate. Well, and it can be modified in the future. The tuples is basically the same as list, but a tuple cannot be modified. And a dictionary, it's another very useful structure that it's unsorted, chunkable, and the difference is that the mainly difference is that it's indexed, and it does not accept duplicates. For example, here we define a list with the elements metformin, glimepiride, and empagliflozin. I know you know what have in common all these drugs. They are antidiabetics. Well, another thing is that I try to make this course very focused on drug discovery, because sometimes when we are trying to learn a programming language, we can find a lot of examples online, but we cannot find examples who manage the data that we are used to. And at the beginning, this was very difficult for me. So let's define this list. If we want to see the result, I did something wrong. Come on. I find my mistake. Okay. So now we have this variable. We're going to define another list, but if you can see, this list contains strings, characters, and things contain integer. Let's visualize the list, and we can also visualize particularly elements by the index. Let's remember that Python store count on 0. So this is the 0 element, this is the 1 element, this is the second element. So when we print this,
which value do you think I'm going to get? Metformin, because it's the 0 element on the list. So you can think this is very easy, and you're right. But it can help us to make an introduction to Pandas library. Pandas, I know you remember this name because it was on the list of dependencies to install. Pandas is a high-level data manipulation tool, and its key structure is data frame, which is basically a table. Data frames allow you store and manipulate tabular data in rows of observation and columns of variables. So now we are going to import pandas and import NumPy. And do you remember antidiabetics and doses, which are lists that we defined on the previous cells? And we are going to storage this on a dictionary. This is a way to define a dictionary. We use a key and a value. And now this is the result. But this is a very different structure from a table. So a very easy way to convert a data frame in a table is use this command from pandas. So now we are going to define our data frame by use the command pd dot data frame dot from dict. Let's remember this variable it's a dictionary. And let's visualize the result. Now we have a table with I like very much pandas and Python because you can structure data in a very simple way. Let's remember that antidiabetics were just a list, and now is part of a data frame, which is not just very easy to manipulate, it's very easy to analyze from us. So I know I want to show you a way to visualize a specific column of a data frame. You use you use the corchetes symbol. Sorry, I don't remember in English. And you should use the name of the column you want to visualize. Now, if you don't know the specific names, you can call the columns method. No, you can use the columns method and get the variables. No, it's not very difficult to identify the columns names, but in the next session, we are going to have many different columns names corresponding to different descriptors. So I guess it's something you should know. Also, there is a way to visualize a specific row with the method lock. Oh, sorry, this didn't work.
Barbie, we have another question from
Okay.
Arley. He doesn't know why do you need to write SPD and as NP when importing the libraries?
Well, actually, it's not necessary. It's just that sometimes when we call, for example, the data frame method, if we do not call it as PD, we should write pandas instead of PD. So
okay,
this is the reason. Just to make easy the use of the library methods. So moving on, in this cell, we can visualize a specific row. Remember that the first row on the data frame, it's going to be the 0, 1. We can also look from the second and etc. So to visualize, for example, a specific cell, the result, here I'm asking to pandas to bring the first row on the column drug. The first row on the column drug should be should be glimepiride. Let's verify if I wrote this code fine. Yes. So if you can see, pandas allow us to manipulate the data in a very easy way. Also, we can make the inverse process. We can convert a column to a list. I'm going to storage the drug column in a list which is called L, and here is the value. This list is exactly the same that the antidiabetics list. Well, now we have learned how to create a data frame from a dictionary and create this dictionary from list. And we have been working a little bit with this process of get some specific information from the data frame. And right now I'm going to show you how to load a CSV file, which is also basic, which can be via an Excel file or a text file into a data frame. So thanks God, pandas has a method who allows us.
Sorry, we have a question. What is the difference between log and elog?
Log and elog. Ok, es la indentación, porque en ilog puedes especificar en... Espera. Sí, es la indentación. Si tú conoces los nombres de las columnas, o más bien los nombres de los índices, puedes usar ilog. Perdón, puedes usar log. Entonces, esta ilog sería más bien para visualizar celdas, para visualizar filas. En un data frame, in a data frame, the vertical data, it's known as columns. The horizontal data is known as rows. Okay. Is there any other question, Agustin?
No, we are right.
Okay. So no, we were talking about how to read a CSV file. And it's very easy. For example, here I have a folder called data. Here I have all the data we are going to use in our problems. For example, this. You can see that it's a text file, and we are going to convert to a table by using pandas. So we are going to storage all this information on the variable b of a kim. And to visualize the response, it's here. So it's a very beautiful way to organize the data in a data frame. B of a kim, I include here the results. sorry, I include here the reference. Biofakim is a database of Mexican compounds with biological activity, and there are many types of compounds and very different compounds. For example, we have compounds from different kingdoms. I mean, we have compounds isolated from fungus, for plants, and others from from propolis, etc. But here the important thing is I want to show you how to manipulate and how to get information. For example, if I look here at the kingdom values, I just see that I see there are many fungus, propolis, but it could take for me a lot of time to identify the unique values, and I can do this with the unique method. I'm just show you some of the most common pandas tools. And for example, if I want to visualize the entire column, I can use the Biofakim, I can use this command. And here are all the values. And also remember, you can do it on this way. And it's basically the same. Okay, so is there any other question about this?
Nothing on the chat.
Nothing on the chat. Okay, so I guess that it could be, so it's time to take a break.
Okay, so welcome back, everybody. I guess that you have some time to watch to think about the information. Do you have any question about the concepts we discussed previously? I'm waiting for the chat because actually right now I'm watching the chat. When I share my screen, I can see the chat, so that's why sometimes it's very difficult to answer your questions. But Agustin and Lilian are doing an excellent job, and I want to thank. Well, okay. Does everyone else know the GitHub repository? I can share again. You can download all the information from this. Okay. Sorry. I'm sending you again the GitHub repository when all the notebooks are stored. And if you download the dependencies, you can run by yourself on your computer. I'm going to start sharing my screen to start working on our first notebook. Just give me a minute. Okay. So this is the first part of the practical session. Well, just the first one. Okay. Today we have a particularly objective with. This objective is build a machine learning model to predict the biological activity of compounds against bromodomines, specifically bromodomines type 4. Something I want to emphasize is that the machine model is the result of trained an algorithm. Is the result because the model saved the information of the training process. So it could be understanding at the same time, but it's not. The model is ready after the training process. The data that we are using are compounds with known biological activity against bromodomines. The activity was computed with the fluorescence polarization assays. And it's very important to define the target that we want to predict. In this case, it's going to be the logarithmic activity 50. This value, as you can imagine, has float values, and of course it's a numerical value. The fact that we use numerical value means that we need to use a model which allows to predict numerical intervals. It could be a linear regression or also a super vector machine regression. But in this case, I have decided to use a linear multivariate regression. So I guess that this is very important because before I start writing the code, we have to identify which data we have and which is the problem we actually want to resolve. Okay, so the first step, everything we are going to resolve a code problem is to call the Python libraries that we are going to need in our process. On the past session, we were working a little bit with pandas to manipulate the information. NumPy is very similar. Also, in this session, we are working with two visualization libraries that are Seaborn and Matplotlib. I use this line, Matplotlib inline, because this line allows us to visualize plots on the Jupyter Notebook cells. So the next step here is to load the data. Okay. We are going to use the read CSV file method. This data is storage on the file data. That's why you can see that the root of the file. Maybe in your computer is a little bit different. Okay, I'm going to do. Okay. And now here we can visualize all the data frame. Or you can use the heat method to visualize just a few of the components. For example, if I write 5, I will just visualize the first 5 rows. And here I can identify the information that is present. For example, the target bond name or the protein, the assay type, the most important thing, the activity value, which is the target of our problem, and many other numerical descriptors like the molecular weight, the log P. All of these variables are chemical descriptors. And for me, it was not very easy to implement machine learning models to my research or to resolve problems from my lab, because there are many good examples online, but I couldn't find 2 years ago chemical examples. I mean, there was, for example, a lot of papers, but not all of them share their code. So it seems like a very huge difference to me to implement my own data. that's that that's why I hope you will enjoy this work, because sometimes it's very easy apply the Python code if we know how to use Python, but it's not very easy to apply them to a specific data. Okay, so let's continue. I want to show you that all the information, all the activity information correspond to the same assay. This is very important because if the information comes from different assays, the model it's not going to have a good performance. In this case, we see that the unique version of the column desk name is always fluorescence polarization. So all the data comes in the same format and was computed on the same way. Also, let's verify that the type activity is the same in all the cases. So we do not have to make any other treatment about the activity, about the target. And right now I want to start working a little bit in exploratory data analysis. I mean, this is a very important step because we can't, in this part of the process, identify which variables are high correlated and which variables are correlated in a positive or in a negative way. And we also can identify if two variables are correlated between. For compute the statistical descriptors of the numerical data, we are going to use a pandas method who is called describe. So when we run this, tell me.
Arley has another question that is,
okay,
how was activity calculated? And what does it actually physically and chemically represents of the compound?
wait. Sorry, the question was about the activity or about the descriptors?
How was activity calculated?
Okay, activity. Okay, this is something important because this activity I didn't compute. Do you remember that I told you that it's very important that there are many data sets available and free available from drug discovery? So the data information, you can get the information on this page. It's also a paper. I get this data from a database, and they, for example, report information from different assays. But I just choose this one because I need that they come from the same assay. So to be honest, well, this data is not mine, but this data is reported in a paper.
Okay, there's a second part of this question that is, what does it actually physically or chemically represents of the compound?
What represent of the compound? Well, it represents that these compounds are able to modify or to inhibit the promodamine's protein.
Okay.
Okay. Well, okay, so get the statistical values. And here is this is something very beautiful about pandas that allow us very quickly compute statistical values. And for example, we can see the mean of every of the activity, that is 5.2, the mean of the molecular weight, the standard deviation, the minimum value and the maximum value. For example, we can see that the number of rotable bonds has a minimum of 2 and a maximum of 8, etc. We can explore all the values. And in Jupyter, sometimes it's a little bit different to identify all the columns that are on our data, but we can use the columns method, and here we can print out all the columns present on this file. And as we can see here, some values correspond to strings, and some others correspond to numerical values. Even numerical values can be different themselves. For example, this variable has integer values, and this has float values. But to easily identify what type of data is in our column, we can use the types method. You can see, for example, that activity of course is a float, molecular weight also is a float. And here the question is, which kind of types should I include to build my model? Do you think smiles is going to give us some information, some significantly information, or the compounds ID could affect in any way? Of course not. So we are going to work a little bit on select the numerical data that it's going to be the input data to feed our model. We can easily use the select the types model, and we are going to specify that we want the float and the int data types. Let's run this. Okay. Here we can visualize all the columns that proportion interesting information, but we need to storage all this information in a new variable. This variable is going to be the numerical data. So we just create a new data frame from all the information. Unfortunately, there are still some variables that we need to drop out. For example, the compounds ID, because even when it's a numerical variable, it's not going to give us any information. And right now we are going to compute the correlation matrix. The correlation matrix, what's done is that measure the linear correlation between two variables. Okay. Here we have, wait a minute. Okay. And the correlation matrix looks like this. We can visualize that the values goes between 0 and 1, and also they can be positive or negative. Of course, a positive value means that if variable 1 goes up, variable 2 also goes up. And a negative significant that if one variables go down, the other one goes up. So it's very important because when the value is closer to 1, it doesn't matter if it's positive or negative. It means that the variables are highly correlated. Now, this table, it can be visualized as a heat map. A heat map is a way to represent information with a color scale. The color scale is right here. Sorry. And for example, the activity is highly correlated with activity. This is very obviously, but here we can identify some variables that are highly correlated in a positive, which are the colors close to white, and in a negative way, which are the values darker, in a darker color. For example,
David has a question now.
Okay.
How are you dealing with data consistency and quality? Can you tell us a little bit about the collection and pre-processing phases?
Okay, I guess, honestly, I didn't work a lot with this. Why? Because wait. Okay. We can just make a session of how to prepare your data. But I think that in this case, it was better to work with the implement of different type of algorithms. Yes, so this data is not very processed. This data, actually, I didn't process. It was a student from the lab. But I have not all this information right now. I just can tell you that we were from the database, and we get the information we hope it will be useful. And after we with the smiles, we compute all the descriptors which we submit. But for example, I am not even doing the standardization process here because this could take too many hours in a workflow, in a workshop. So I'm sorry, I do not have all the information right now.
Santiago has a comment, I think. It says, I think that those things depends in the experimental part and have to be evaluated independently. When you are sure about your experimental data, you can apply these procedures.
Okay, Yes, that fact is very important because you cannot use data that is not confiable. I don't remember the word, but
Trustworthy or something.
I'm also using data who was published, and I assume that these values were correctly computed because seguramente si no hubieran dado muestra suficiente de la forma en la que calcularon sus valores, no hubieran podido publicar su artículo. So this is very tricky, but I didn't do these essays, but I get that from a confiable source. Is there any other question?
Not right now. Thank you, Bárbara.
Okay. So, okay. Here also, well, from this heat map, we can identify highly correlated and uncorrelated variables. Now, if we keep many correlated variables in our model, we are going to deal with a problem called overfitting. The overfitting is when there are too many variables who apport the same information of the model, and the model cannot identify different information. So before of continue, I want to show you how this exploratory data analysis can help us. For example, here I'm doing a scatter plot of the activity, of the activity versus the lipophilic efficiency. And we can see that they are highly and positive correlated. Well, this is not a correct correlation, but we can see that there's a tendency on the data. So right now we have created a numerical data frame to storage the numerical data, and we need another one with the target information, that is this controversy activity. And we are going to storage all the information, and we are going to specify that we want this column to be called in the same way.
Sorry, Barbie. We have a question about how many descriptors and how many biological activities are you using? Just I want to know the ranges.
Okay, wait a minute. Okay, I am using, well, of course, let's remember this is just an example. I mean, this is not something I can publish, I'm going to publish. This is just information I identified as significantly to build an example. I am just using 14 compounds. And I am using 12 descriptors. And there was another question, I guess.
Yes, about the ranges of the descriptors, I believe.
The ranges. Well, this information is completely here on the described data frame. For example, data, I mean, if we see the mean value and the max value, we can identify the range there of all the descriptors. You know, is it clear, or do you want to talk more about that? It is a little bit difficult to me because I cannot see the chat on my screen when I'm sharing the Jupyter.
We don't have an answer yet. If you want, you can go on, and in case there's another question, I'll let you know.
Thank you very much. Yes, if you think that I am not answering your questions, you can send another message.
Bárbara, if you want to try to see the chat during when you are sharing your screen, on the top of your screen, it will appear something about Zoom, and then you see the option chat, maybe in more, something like that. Do you see it?
Okay, yes.
So you can see the chat, but
Sí,
we
ya
are not
puedo verlo.
seeing it. So it's not interrupting our vision of your page, okay? Don't worry. Thank you.
How many biological activities? I'm using one because I cannot make now I see the question, just one, because the information from different biological tests says very different things. Maybe with a further study, we can find a way to make an harmonization of the data, but right now, with this kind of model, you can just predict one target. And in that target, all the data should have the same values. So it's like when teacher says, no mezclar manzanas con peras. Okay. So, okay. Now that we have our data to train our model, we need the labels. Okay. We can, this is why Pandas is very useful, because we can create a new data frame with the target information, and we visualize just here. Now, for example, the range of the data can okay. I guess this completely answered this question. The 50% have a value of 5.2, the max value is 6.2, and the minimum value is 4.5. Okay. So now, don't forget to drop the activity column from the numerical data, because we just want data that is very representative. And if we include the target on the training set, this model is not going to have a good performance. It's going to be very overfitted. And now that we have split the data, now that we have separate the targets and the numerical data, we are going to import the model. In this workshop, we are going to work with methods built from a very popular and open source Python library called scikit-learn. For example, we are not going to code all the process. We are just going to import the models built with scikit-learn. Sorry, what did you do in the last step? Okay. in the last step, I separate the inputs and the labels. Maybe it's going to be a little bit more clear on the next steps. Okay. Now, the model just learn from the things we teach. So it's important that we split our data into training tests in a data test in data test. The train test it's going to be to compute the parameters model, and the train test is going to be useful to measure the way the model is performing, how good or how bad. But we need components that the model have never seen before. So this step is very, very, very important. We are going to create these variables with the method train test split. I mean, from the data we have, we are going to separate them into two sections: the train section and the test section. And the percentages we are going to use is 30%. So 30%, 70% it corresponds to the trained, and 30% correspond to the test. Okay. Okay. Now visualize what kind of information do we have on X trained variable. This is a data frame with all the numerical values we identified in the last steps as useful variables. Yes, and as you can see, those are all chemical descriptors. Also, you can see that this variable has exactly the same column information but you can see that the IDs are different. So randomly, we select some compounds to teach our model, and randomly we have other section to test the model on the next steps. So, what do you expect to see on the G-train? Which is our target? Now that I can see the chat, I guess that some volunteers can answer the questions on the chat. What do you expect to see on the G-train variable? No one? Ay, creo que alguien. Right. The same as in X, but similar. Not necessary, but thank you very much to answer. What we expect to see is the target information. This is the activity information. And this also has similar values to the complete data set. So in X, we have the numerical data, and in Y we have the activity that is the target. This is very, very important because To implement the model, it's actually very easy, but we have to be sure of what information are we include in the model. So, to import the linear regression model, we need to run this cell. What I'm telling is, come on Python, from scikit-learn and linear model modules, bring to me the linear regression. Now, I am going to save this method in a variable to make easier the manipulation. Okay. So now LM variable storage all the information from scikit-learn, and this is when all the magic happened. I just run this command and my machine learning model it's trained. But it's very important to split the data because, for example, we have to add this information in a very specific order. You can see the parameters of the model on the scikit-learn documentations, but in all the models that I have, in all the supervised models, you first insert the information of the training data, and after you insert or you write the information of the target. So now let's figure out some information about the model. For example, we are going to identify the coefficient values that the model assigned to each descriptor. Those are the coefficients. This is the way each descriptor contribute to our model. So this is not very information. So let's represent on a data frame. Also, we can sort by. Creo que lo estoy haciendo. I'm not doing this properly. So, but now we can identify how much each descriptors apport to the models. Can you tell me which is the descriptor that apport with a bigger way? Thank you, Arlie. Thank you, Arlie. It's lipophilic efficiency. So actually, these models does not have a very proper performance because lipophilic efficiency apports very much. So a very good idea is to drop this variable. Yes, has the same. So I mean, it's one or another one. To tune the model to make the model more precise, we need to change the data con la cual lo estamos alimentando, and This is the most important part of develop a problem, of develop a model, because actually you can see that it's very easy to implement. What is not very easy is to offer a good model. But let's continue to, I want to, sometimes for me it was kind of hard because I said, well, this is the model, and now how can I use it? Let's use, in this cell, I bring, I wrote, sorry, a function to bring information, but for the original data set. So this, I wrote an ID, and it gives me the numerical data information of a specific compound. For example, for the compound with the ID 1603, we have this information. We can use this information to feed our model and to get a prediction. And this is very easy to use because scikit-learn built the predict method. So we just feed, let's remember, test correspond to all these variables. So if we predict this, it says, okay, your model could have a value of 6.2. Now let's figure out how far of the reality is this. This is the predicted value. I want to know the real value, the value that is wrote in my database. So let's use this function. And the real value is 6.2. What can you say about this? Has the same value, is perfect. Yes, it seems. Actually, our model is very far away to be perfect, but in this particularly case, it works. So what I want to show you with this example is a way to build a predict model with a linear regression. So now we are going to write a report with the information that Santiago just said, that for the compound with this ID, the real activity, well, the predicted activity is this, and the real activity is this. Okay. So let's continue. Okay, so now you can be wondering why we split the data on a train test and a test section. So we are going to compute all the predictions. Yes, come on, Isabella.
Can I use my mic?
Yes.
So I just don't get why you are using linear regression, because you can just correlate two variables. You could use more sophisticated methods. I don't know.
Okay, the answer, it's not going to sound very good, but the answer is like, because I assume you don't know how to do this with scikit-learn.
Okay.
Yes. I'm sorry, maybe this is not what you were expected from, but
No,
I
okay.
wanted to show you how to implement a machine learning algorithm to make a machine learning model with Python and scikit-learn.
Okay. I just thought, what's she using? It's not the best, but okay, it's just an example. Fine.
Yes, it's not. This is just an example.
Nice.
Another thing is that if, for example, I should have more data here, but if we have more data, the model can take hours to be trained. So
But
this is just like a little bit example to show you how to implement the code.
But in your projects, what do you use?
Excuse me?
In your projects, what do you use? What model? Which model?
In my project, well, actually, I'm trying with logistic regression, and I'm doing super vector machine classification, because in my project right now I'm not making regression predictions. I am just trying to classify. To classify a model in a specific class.
Okay, thank you.
Okay, thank you, Santiago, for your comments. Okay, I'm very sorry, Isabella.
No, that's okay. I was just curious.
Yes. So let's remember to the prediction section. We already did a single prediction, but let's remember that the GTist has many other components. To be specifically, has has 12 components. So an automatically way to make the predictions is pass this variable on this method, and let's see what the result is. Those are the results for the test. Now let's make a scatter plot, and no plot. Here I'm plot the GTs, the real values, and here I'm plot the predictions values. So it seems our model performs very good, but this is because the decision or the weights are basically computed with two variables which support a lot to the model. So now, when we do another way to see how good or how bad look our models is plot the residual values. That it's the difference between the real and the predicted variable. And in a perfect model, we should get a Gaussian distribution. So it seems it's more or less, right? Now we can work a little bit more with compute some specific metrics. Do you remember that I say that if we had different type of algorithms, we also have different metrics for each kind of algorithms. The most commonly used from regressions are the R-squared, which is the coefficient of determination, and also the root mean square error. And again, it's very, very easy to compute these metrics by using scikit-learn. We just import this code from the original Python library. Also, I include here the link to go to the official documentation and see how they are implemented. And we are going to compute the coefficient correlation by use the G-test and the predictions values. So that's why it's very important to split the data, because if we do not split the data, we cannot measure how good or how bad our model is. Well,
we have a very high correlated model. So now, a typical performance metrics for regression is also root mean square error. It gives an idea of how much error the system typically makes in its prediction, which a higher weight for a large errors. O sea, a bigger RMSA correspond to bigger errors. And another way to measure a difference between vectors or difference between regression models is the mean square error. And we also can use the MSA. So let's figure out. So these metrics can tell us how good is our model, but what we really need to do is to compute another model and then choose the which one who has the better metrics. Super okay. I'm going to ask, so yes, Cecilia, support vector machines can also be used for regression tasks. I do not have an example here, but it's very easy to implement. So, well, this is all I have from this section. And can we take 5 minutes? Okay. Okay, sure. Okay, I will be back in 5 minutes. Hi, everyone, I'm back. Well, answer to Ricardo's questions, I suggest that root mean square error is a more appropriate metric because this is more sensitive to outliers. Sometimes it's easier to analyze the models with MSA because it's on the same scale that standard deviation, but it depends very much on of your models. So you cannot just train one and say, well, this is the best. So now let's continue with another common technique, which is also an old technique, but I still like to use it. And I will tell you why in a while. The next algorithm we are going to work on is decision tree. Decision tree, it's a very versatile algorithm, and it's very important because they can perform both tasks, regression and classification. But regression trees only works for supervised learning. We should know the labels first. It has several advantages. The most important advantage is that they are very easy to understand because can be visualized as a graphical representation, and they are very intuitive. Also, the result can be visualized in a image. We are going to do it in a few minutes. They are also good. The mainly characteristic of this algorithm is that it's
very useful in data exploration because it gives us a lot of information of how data could split, and also requires less data cleaning process. These models are not sensitive to outliers. And another important thing is that data type is not very important. I mean, in these particularly models, we can use a numerical and not numerical data. The mainly disadvantage of this algorithm is that it's very common, the overfitting. So now we have a different data set, or the objective of this practice is to build a machine learning model to predict if a molecule has drug-like properties. The data I include is ADME descriptors for 3 different libraries. Those libraries are 2 of natural products, the IFRO database and the Biofakim that we saw in the first practical session, and a subset of the approved drugs for FDA. So, do you remember that in the other example, do you remember that in the other example, the target was the activity? Here, the target is a binary classification. We assign 1 from the positive success. The positive success corresponds to drug-like. Of course, drug-like are the subset of approved drugs. And the natural products correspond to the 0. I am just doing a binary classification model. In this case, we have some ADME descriptors like aromatic heavy atoms, H-bond acceptors, H-bond donors, heavy atoms, rotate bonds, and different solubility metrics. So, first of all, we are going to load the data and storage on a data frame. This information was computed from Noemi Duran. I include her contact information here. He was a student on our lab, and he was working a lot with the ADME process of natural products. So some of the that data he computed, I am using for this example. So let's visualize the information. As you can see, we have several descriptors here. And for example, on the library column, we can see the 3 types of data sets: AFRO, Biofakim, and FDA. So let's remember that the target, or the column we want to predict, is the compound has drug-like descriptors or not. 0 for no, and 1 for yes. This is very important because sometimes it sometimes seems that the problem is very difficult, but we can separate in small pieces to resolve one problem at a time. So here I include a box plot of molecular weight, and we can see that B of a Kim has many outliers from these descriptors. In this case, I don't need to remove them because this model is not sensitive to outliers. And we can do the same. We can do the same visualization for any other descriptor. So again, again, let's identify the numerical data. And compute their statistical values. And now we can compute again the correlation and visualize. I really like heat maps to visualize correlationships because it's easier to identify values similar to 1 or to 0.9 on this table. I hope you will agree with me. And well, previously, I do the task of identify many correlations variables and storage all of them on this variable. You can see, for example, that we had many ways to describe the same. For example, the molar solubility or the solubility expressed as milligrams from milliliters, etc. So I'm going to drop all this information from our numerical data by using the drop methods of pandas. And of course, I need to drop the target column. You choose the one control. Not necessary, Monica, because maybe we have a variable who can apport more to the model, but it's a little more hard to compute. So I don't think that the computational requirements should be a good should be an important thing at the time of identify the variables. Okay, so now we have all this information to train our model. And now that we have the information to train, like this is another supervised technique, we need to storage the DF target result in a new data frame. Remember, our target here is the drug-like column. And visualize the result. Okay. Now, this is everything we need to train our model. Okay, again, we are going to import the train test split to separate the model between the test and train section. And we are going to import from scikit-learn the decision tree classifier methods. And also, maybe this is sometimes kind of hard to install on your local computers, the module export graphics. For me, it was easy to install with Conda. And again, we are going to split the data. So I include a random state because this method it's random. So when you set the seed in a particularly number, you can split the data on the same way always. So if you repeat this on your personal computer and you do not include this, maybe you can get some different results. So the test split, the test size could be different. Usually on machine learning, it's the 30% or 20%. I'm going to set on 30%. Y algo falló. I didn't run the cell. Yes, for replicability, a set must be set, David, because you can get very different results. So let's visualize our train information. And visualize our target train information. Let's remember that those are values of 1 for success drug-like or 0 for not drug-like. And here it's very easy to assign the model. Let's remember that always the devil is on the details. What I mean that machine learning methods can get very different results with very different set of configurations. So first of all, I want to run a model with any configuration, just the default configuration of the methods. And let's visualize what happened. So I assign my model with any set of configurations and try something. This works perfectly yesterday. Okay. I'm going to restart the kernel. This, the Rebel method. Wait. Okay, ya funciona.
Maybe it's as Stella Mari says, maybe the last parenthesis that's commented. I know you added.
No, it was not about the parentheses. It was about a data type problem. And now it's fixed, but honestly, I'm not sure why, because I run the cells like without do any modifications. The NP-Rebel method was used to convert to convert the target to a NumPy array. And to make easier to scikit-learn, identify the the structure. Okay, so now we fit the model. This is very similar in all the scikit-learn models. And here is important to include the information on a very specific way. For example, first always is going to be the parameters, and after the targets. And we are going to use these methods and these libraries, export graphics and PyDot, to visualize the decision tree as an image. Now, I need to storage the numerical data columns on a new variable to make easy to Python represent this information. If my computer works. Genial. Okay, so now this section of code, it allows us to visualize the result of the decision tree. With the export graph bits, we insert the model, the trained model, and the features names. That's why it was important to define the name here. And also we can storage we can save the image on our computer. So here it's kind of different. Identify some particular the particular ways that use the decision tree to split the data. So let's get back here and include some specific configurations. For example, I want a max tick of 4. And here is the result. This is a very intuitive and a very easy way to analyze the data. How this works? Scikit-learn choose a variable and split into 2 different sections. And the idea here is to get in each of these nodes very similar compounds or very similar elements. For example, the elements that are here are more diverse than the elements on the last node. I like this because, for example, we can, thanks to this decision tree, we can know that the probability of that a compound with a value higher than 1.5 is a drug-like compound. It's very down. So for a start, we know that our compounds should not have a value higher than 1.5. And this information, I guess that for us is very valuable to design drugs with better drug-like properties. No, the way that this perform the split is with the Gini index. The Gini index is a way to measure inequalities, or a way to measure the dispersity of the data. Values closer to 1 indicates very inequality, and values closer to 0 indicate inequality. And in this case, for example, we can see that the values of these compounds
indicate that are more that are less diverse between them. So in each node we have very similar compounds themselves. So if we change for example, if we change this again, we can get very different results. You see? And of course, we want to make some predictions with these models. For example, let's predict if the acetaminophen is identified by our model like a drug-like or like a not drug-like. Let's perform a single prediction. And the result is 1. What does mean to get a 1 as result? So according to our model, acetaminophen is a drug-like or a not drug-like? Yes, it's a drug-like. Remember, 1 was assigned to successful case. So let's continue with let's continue with the predictions of all the test set and some other metrics. The accuracy for this model is of .8, comme ci, comme ça. And the confusion matrix. In this case, our model is not very good because it's predict the true positive results are just 133 and the but we are also getting 36 false positive results. So here we can play with the initial setups to get a better results. Here the idea is not to get any false positive values. And let me get back here. I want to show you how the confusion matrix works. Okay, the confusion matrix is a way to count the number of times that instance of class 0 and class 1 are classified. In a perfect classifier, we have only true positive and true negative values. So a way to turn or to improve your model is to increase the name of true positive values. So now let's continue with the
next algorithm, who is the random forest. A random forest equal to decision trees allow a regression and classification. And a random forest is not any other thing than an ensemble of decision trees. I mean, we train, well, we not, the model train many decision trees and combine the results to offer a better result. So let's call the model from scikit-learn. And here we can say the model how many decision trees we want to train at the same. In this case, I include a value of 100. And let's fit. But the disadvantage here is that we cannot observe the result in an image like in the previous step, because we cannot plot graphically 100 decision trees at the time. And now let's predict the acetaminophen result. It's also 1, so it performs kind of similar. Make all the predictions and print the confusion matrix. So the true positive here were 133, and here we get 173. What information can we get from this number about those models? So this is the reason it's better to use random forest than only a decision tree. But random forest does not show us the information in a representational way. So I recommended you to use decision tree to explore your data, but to make better predictions, I recommend you to use random forest. Any comments? No, it's everything okay?
I have a question. I'm not from this area, but I know that you're showing just an example of all of this. I wanted to know if in the real world, I mean, if I have a project doing it, everything will run so fast, or we have to wait many days for it to run?
No, we have to, not days, but maybe hours.
Oh, okay.
Maybe hours, yes. This is just a tiny example. I hope you can have many information from your project. For example, in my project, once a model was running for 10 hours. So not always is very quickly.
Okay.
And it maybe it depends on your computer, but the good thing about machine learning, and specifically the good thing of scikit-learn, is that performs very well with CPUs. So, well, I don't know in your case, but in some laboratories, we do not have many graphical computers to train deep learning or neural networks, but we can get a lot, we can work on good models by training many different machine learning models.
Okay, thank you.
No, thank you. So is there any other comments? This is kind of funny because once we learn how to work with scikit-learn, it seems very, very easy. And obviously you can after make your Python scripts to automatize these tasks, and maybe trying at the same time the different models from the same data, but with many different configuration setups. For example, you can run at the same time different nodes, or even different split data process. For example, instead of make always the process with 50%, make it with 7%, etc. So once you know how to implement this, it's very easy to modify your parameters. So Lily, can you stop sharing my?
Yes. Done.
Okay. Now we have worked with two different supervised models. Well, actually three regression models, decision tree, and random forest. I want to show you now how to make a representation of the chemical space with a unsupervised technique called PCA, principal component analysis.
Great.
But I want to share a different screen, so that's why I ask you to. Okay. Just give me a minute. Ay. ¿Dónde está mi Zoom? Okay. Just can someone tell me if you are seeing my screen again?
Yes, we are.
Okay. Here I want to present you a very little different example, because this is a Python script we built in our lab to make easier the visualization process. And I'm going to show you the result first. This is the result. Maybe some of you are familiar with this kind of representation of the chemical space, because those are very easy to analyze in the fact that are a two-dimensionally plot. Here I want to present you the result of some libraries for ADME descriptors. We have the FDA, again, Biofakim, the data from Afro. Do you remember that those libraries were the which one that we include in the previous example? Also, here we have the Nube database, and the library that includes the compounds, natural products from China. So here I'm showing you the distribution of these different libraries based on their ADME descriptors. The idea here is to analyze which library has the most similar behavior to FDA. And of course, is not the China. We can see, well, we can see that the space that cover the FDA compounds, it's very located with some exceptions, but the SMA has a higher distribution compared to other libraries. And I like very much this example because you can identify the name of the compounds. For example, from Biofakim and FDA, we assume that compounds that have a different, that has similar distribution have also similar descriptors. So they are going to have a very similar ADME process. For example, in this case, we have this Selachinella from Biofakim, and it's similar to darunavir. Now I will show you a little bit more about how to convert the data from different descriptors in a two-dimensional plot. So does someone has any comments about it? I can see the chat right now. So, no. Okay. Here I'm going to call another algorithm from scikit-learn, which is the composition. The composition allows me to perform a principal component analysis. And this is very much like the past models. For example, I assign the model to the variable scikit-learn PCA, and I say that I want to get 3 components, or just 3 dimensions, and the data, it's the same that in the past example. And if you remember, we have many descriptors, and we are going to use a reduction technique to visualize in less dimension. But here, the label is not important. The label is just to be useful to color the results. But the model by itself is going to group the compounds. So here we separate, we storage the numerical data that is going to be useful for the fit the model, which is this link. And also we can get some informations like the loadings that are the values, are the ways that each component contribute to the model. So here, no, I'm going to show you this. In this example, I'm importing from these files some functions. And these files are built with Python and scikit-learn basically. So we are going to load the data. And when we run this, run this function, we can identify, we can get the result. And as you can see, now we have the component 1, the component 2, and the component 3. These correspond to new coordinates. And these values are the ones that we use to plot the information on this graphic. So, unfortunately, we cannot get all the information back. We lost information when we do dimensionality reductions. And with the component 1, we recover a variance of 38. No, this script is not in the GitHub right now. I'm sorry, but in the evening, I will update. So no, so sometimes a common problem in our lab was that people think that this plot was immediately a result of the PCA, but not. The result of the PCA is this data frame. This data frame tells us the new coordinates of the compounds. And now we build another function to plot the results. And here we say that in which color we want to represent each library. But the color is not given by the model because the model doesn't know the labels in the beginning. So we can here see the variance that we recover from the model. And I guess this is another very useful tool to drug design, because here we are plotting the ADME results, but we can also plot, for example, the docking results and many other descriptions or any activity values, etc. So, Lillian, I guess that we are ready for other break of
Fine.
20
No
minutes.
Okay, I'm gonna write here.
Hi, everyone, again. Let's continue in the final example of this workshop. I hope you have grabbed a couple of coffee or something. Okay, so let me share my screen. So, I hope we are always here. So let's continue with this last example. We are going to perform a supervector machine, specifically a classification one. This, well, first let's remember what is a particularly class. A class is, a class corresponds to an element who has something in common. And classification algorithms help us to identify to identify the element in a particularly class. So the classification algorithms has many advantages, particularly supervectors, because this one allows us to perform classification task and regression. Maybe the linear regression example could perform better if we use a supervector regression. And also, supervector machines help us to find the decision boundaries between the data in a linear and non-linear way. And other particularly advantage is that we can use them for complex data. I mean, we can use them for the use of many descriptors. But of course, this algorithm also had many disadvantages. The first one is that it's not very suitable for large data sets because it can take hours or even days to train a model. But so another disadvantages in this context is the training time, and finally, an, an issue that is not necessarily a disadvantage is the kernel. The kernel is the way that we use to find these decision boundaries. But some types of kernel makes that training a model takes very long time. But how does it work a supervector machine? The main objective of this algorithm is to segregate the given data set in the best way possible. The distance between the nearest point is known as margin, like we can see here. Okay. So the objective is to select an hyperplane with the maximum possible margin between the vectors of a given data set. Let's see this picture. In this picture, we have two classes, class A and class B, and we have different hyperparameters. In this case, it's very obviously which is the best hyperparameter to separate both classes. So with the hyperplane, the model is going to select is the black one, and the points that help to separate better the classes are called the supervectors. So in a very brief way, this is the work a supervector machine works. So in this problem, we have the same objective that in the decision tree problem. We want to build a model to predict drug-like properties of a single compound. The data, again, correspond to three different libraries, both of natural products and one from approved drugs. And the endpoint is a binary classification. For another thing is that we cannot fit the model with an string target. So that's why we do this switch to 1 for the successful case and 0 for the not success, because we need to fit the target with a numerical value. Any comments? No. Well, the ADME descriptors are the same that we already know because we are using the same data. But here, the method is different. We are using SVM. So again, let's import the Python libraries and load the data. Visualize the data again to see if there was if something went wrong, but once again, let's identify the numerical So this section of the code, it's why I import NumPy, because it can help pandas can help us to manage the data, but to identify a specific type of number, it's very useful NumPy. And in this section, I didn't include the correlation matrix because we analyzed previously. And the correlation variables are exactly the same. So I'm going to drop these variables storages on this list from the data frame. And also I'm going to drop the target variable. And get the data to train the model. Now, once again, let's go into storage the target on the on a new variable. This variable is called df target. Okay. Now, let's import the train test split method. Split the data exactly like the same. And let's call the classification method for supervectors. If we are going to perform a regression, we can import SVR, but this is not the case. So now we are going to assign the model to a specific variable. And let's fit. It was very quickly, right? So here I didn't include any set of special configurations. So the configurations by default, when we use the scikit-learn method, it's a parameter of 1.0, that this corresponds to a balance between the classes. And something very important is to identify that the default kernel here is the RBF. The kernel helps us to identify the boundaries decisions because it transforms the input data space into a required form. So a low dimension input space and transform it into a higher dimensional space to make easier identify the separation between the data. Also, we didn't, in this example, I didn't set a random state. So when you run in your computer, it could be a little bit different, the result. Now, once again, let's work on write a function to select the scriptures for a single compound. In this, what I am trying to do is to say, well, from the data that you load at the beginning, give me give me all the compounds which library corresponds to FDA, or if we wrote here biofakim, it's going to run the biofakim column, and then it's in this section, it's going to look for a specific name, but we don't want all, for example. Let's print the result here. And here we got all the information from the acetaminophen compound. But remember that we did not try our model with all the variables. We dropped some variables that were highly correlated. So specifically, we want just the numerical data columns. And it returns just specific information. Now, all these variables and their values are going to help us to make a prediction. The result again is 1. So with this model, with the model we have just built, we can predict that the acetaminophen variables correspond to a drug-like compound. Now let's try with some other compounds. For example, let's do the same from the ambroxol. And again, the result is 1. Let's do it again. And in this case, when we make a prediction for the purgic acid, we get a value of 0. So our model predicts a drug-like compound as a not drug-like compound. So maybe there are some things that we can make to improve our model. So I say that by default, scikit-learn gives us a kernel of RBF, but there are other several kernels like a linear kernel, a polynomial kernel, and RBF that is for circulate coordinates. So now let's identify what happened when we try our model with a different kernel. Here we set up a different parameter and storage this in a new variable, because if I wrote here just model 1, just model, and this variable is going to be reassigned with the result of this. So, do you remember how quickly was trying the past model? It was very quickly, right? Just like maybe 1 second or 2. Let's see if the same happened when we change the kernel configuration. It's not very quickly, right? So some people say that this is one of the disadvantages of super vector machines. So this is also why I'm using very tiny data sets to make examples that can be run in just several seconds or minutes. Well, we can wait to get our model trained, and now it's ready. As you can see, the kernel now is different, and to tune or to find your model, you can change all these parameters. For example, class weight helps us when we have very much data from the positive class, and if you turn this parameter to true, he is going to make an adaptable process just to make sure that the classes are balanced. And now let's predict something from our model. Let's try again with acetaminophen. And what does mean this 0? Someone wants to answer? So once again, this is why I suggest you to try many different setup configurations, because it seems that we get a better model with when the initial setups that know that we are changing some parameters. Here, the result says that the acetaminophen has not drug-like properties. And we know that this is false because the acetaminophen, it's a drug, it's an appropriated drug. So now let's continue with the prediction of the X test.
Bárbara, I don't know if you're looking at the chat, but we have another question from Cecilia.
No me aparece ninguna. A ver, is there any way to know which kernel to use? Okay, Cecilia. Gracias. Thank you very much. I saw it. Well, no, there are not a better way to know which is the best kernel. You have to try the different configurations, and also, for example, scikit-learn allows you to program your own kernel. If you have information for previously models, or if you have identified some specific ways to separate the data, you can include your own kernel. But basically, no, there are not a way to know which is going to perform better. Thank you. Okay, so let's continue with the predictions. And let's identify. It gives us many data, like zeros and ones. We didn't expect from any other thing here. And now here, let's work a little bit more some classification metrics. The first one, all of these are computed and imported from scikit-learn. And first, let's compute the accuracy. And the way in that we ingress the parameters is very important. Is the real values and the prediction values. And remember that this real value that composes the test subset, the model has seen them before. They are completely new for the model. And okay, this. Okay, our accuracy has a value of 0.7. It's not so bad, but we can get many other information. This accuracy is generally not the preferred performance measures for classifiers. A much better way to evaluate the performance of a classifier is to look at the confusion matrix. In the confusion matrix, we are going to represent the number of true positive and false positive, etc. For example, here we have the predicted values like 0 and 1. 1, remember, is the success case. And in these rows, we are going to represent the actual values or the real values. So if we predicted as success, an X success, it corresponds to a true positive. But if we predict this as a positive and is really false, it's a false positive. And a perfect classifier will have only true positive and true negative values. So I guess this is the confusion matrix is a better way to get information of our model performance. Let's figure out. This is the confusion matrix, but this corresponds just to the model one. Let's compute also the values for the second model. Does someone remember how we call the second model? Like model/2. Okay. So now we have predictions made with both models. And for example, let's figure out the accuracy of the second model. The true values, the values are the same here, but here. Okay. I think I need a new cell. So for the first model, the prediction has a value of 0.7. And from the second one, the prediction has a value of 0.8. With this information, which one will you choose? The linear or the RBF? The linear is the second one. The second one because of the bigger number. Yes, we can choose the second one because it seems that it has a better performance. But classification models are not very easy to measure. So let's do the same, but to identify the true positive values. No, this does not mean that accuracy is not important, but we have to identify very many different measures because just in these ways, we can improve our model. And thank you very much, Lillian, for your response. So for the first model, here is the result of the confusion matrix. And for the two, now it seems again that we predict more true positive values with the second model. Any other information? But here is something important to see, because in this model, we can better identify positive results, but we identify less negative results. So both models have very different performance. It seems that the first model works too much better to identify negative values than the second one. Is it clear? So,
Barbie, sorry, I have a quick question. In this case, We are looking to discover or to develop a new drug or a new effect, and you would prioritize the discovery of I mean, you would minimize the false positive discovery.
Yes.
You would prefer a higher rate of false negatives rather than a higher rate of false positives.
So now your question is which model to choose?
Yeah, in comparing the false positives and false negatives, you
Well, to be honest,
prefer...
this is why it's kind of hard to identify which classification model is better, because it always depends of what are you looking for. If you are looking for identify the success case, I'm going to go for the second model. But if for any other reason you are looking for the negative results, you have to choose the first one.
Great, thank you.
Right? So this is kind of confused, but that's why there are many metrics to evaluate the performance of a classification model. Another important way is the precision. The precision is the accuracy, but not the general accuracy of the model. The accuracy of the positive predictions. It means how good my model is to identify positive results. So let's see what happened. Look, it seems, let me insert another one. So here we see that our model identified better positive results. Well, that the model that identifies better the positive results is the one. But why? Because we also have here more false positive. So there is not a correct metric to evaluate our model. It depends very much of what are we looking for, and of course that the main idea is also not to get false positive results, because it can be predicted as positive when they don't really are positive. And fortunately, there's a way to combine the precision and sorry. So there's a way to combine the precision of the true positive and the true false identification, and this is the F1 score. The F1 score in this case is for the first model. So maybe it's a better idea to choose the model with a higher value of F1 score, because this is a harmonic metric, but the disadvantages of this is that F1 favors classifiers that have similar precision, but in some contexts does not really care about the way they predict just positive compounds. Okay, so finally, I want to show you the rock curve. This is a way. Well, you have to compute the false positive ratio and the true positive ratio. Okay, here. In this plot, we are plotting the true positive rate. This is the rate in which the model learned to select just positive compounds. Sorry, to select true positive compounds, and this is the way our model can learn to identify false positive. So a perfect classifier should have a compute very different to this. For example, it should be like just one at the same the 0.0. But here we have that the rock, or sorry, the area under the curve is of a 0.8. Ideally, this value should have a value of 1, or should have a value the closer to 1. So as you see, it's very easy to implement models, but it's not very easy to implement good models. But the good thing is that you can build your own workflow or your own pipeline, because the method is always the same. And once you have verified your data and cleared your data, it's very easy to implement very models and find the better one. Okay. Well, this is all that I prepared for you today. I hope this information can be helpful for you and your projects. I'm very sorry if I use very tiny examples, but I want to make sure we can get the result very quickly. And I want to make emphasizing that I am training these models on my computer, so we do not necessarily need a very many CPUs or bigger computers. We can perfectly do this in our laptops. And well, I guess that I have to say thanks to you for your assistance. And thanks very much, Lilian and Agustin, for all your support.
Thank you so much, Bárbara. It was great. I really appreciate your workshop. I've learned a lot.